Okay, folks, I think I'm going to do some of these for y'all so y'all can get a little bit of better idea of how to solve these things. So I'm going to go over 3 problems and I'm going to talk about some key things in each of these. So first I want to talk about how do we interpret what we see in this diagram. Okay, what this diagram is showing us is all the circles with the dot in the middle is the magnetic field. We have 9 magnetic field lines coming out of the page. Okay, so that means the direction of the magnetic field on charge Q, you can see Q is immersed in the field. It's inside of that field. And the magnetic field is shown to be out. So B is out there. And the direction of the velocity, charge doesn't have a direction. The velocity is what has a direction. And the velocity is up. Okay, what this means is that the force is going to be on the x-axis. It can't be on the y or the z-axis. It has to be on the x, so it has to be right or left. If you do right-hand rule, you should get, since it's a positive charge, you should get a force, let's see, to the right. The force should be to the right. Okay, so how do I show this on my paper? I don't have this nifty thing Mr. Parker has on the left. Well, what you'll do is you just take the force acts on the charge. So the force should really be on the charge, shown to be acting to the right. Okay. And that force would be to the right on that charge. Now, the other thing I want to talk about is conversions. We've done metric conversions before. You should know how to convert these units. So let me show you a few of these. This is 3 millitesla. That needs to be converted to 3 times 10 to the negative 3 Tesla. Okay. Some other things. This is microtesla. Alright, so that is 11 times 10 to the negative 6 Tesla. Okay, so use your metric prefix chart. There's one in Canvas on Unit 6 when we first started using it. Alright, so make sure you're using that. I'll show you a few more. This velocity, this magnetic field, this charge, all have to be converted. This is 8 pico, so the pico is 10 to the negative 12 Teslas. This is micrometers per second, so micro would be times 10 to the negative 6. Alright, so you've got to replace that metric prefix with the right exponent. So 6.5 picocoulombs, that would be times 10 to the negative 12 coulombs. Okay, so make sure you're converting all of these. Sometimes I give it to you like this, where it's already in the standard unit. Sometimes I give it to you like this, where you need to convert to the standard unit. Okay, so make sure you're converting. Now I'm just going to do 2 more of these. Alright, this one. Just keep in mind here before we start, this charge is negative. Alright, so that's going to change, that's going to add one additional small step to this problem at the end. But anyway, the magnetic field. The magnetic field is shown by all of these. The idea is that the charge is immersed inside of this field. It's inside of a magnetic field, and all the magnetic field lines are all in the same direction. The circle with the X in it means that the magnetic field is in to the page. So the magnetic field is here, going into the page. It's on the negative Z axis. Alright, and the charge, we'll put it here. The charge has a velocity. The velocity of the charge is to the right. Okay, so we see that the B is on the Z-axis, and we can see that V is on the X-axis. So the force has to be on the Y-axis. It has to be up or down. Right-hand rule gives you that the force is up. When you use the right-hand rule, you do get up as your force. But the charge is negative. So the force is actually down. Okay, and you can see I did a little typo there. That charge is negative. Okay, if it had been positive, it would have been up, but because it's negative, we have to flip our answer 180 degrees. So up becomes down. All right. Let's look at, let's see. I actually want to talk about the direction of the magnetic field for number 9. This is showing the north end of a magnet and the south end of a magnet. The magnetic field here is north to south. That's the direction of the magnetic field. Let's look at number 7. The direction of the magnetic field is from north to south. So here the magnetic field is to the right. Alright. Here the magnetic field is to the left. It always goes north to south outside of a magnet. That was one of our key concepts from last week. So if you're forgetting some of this, if you're not getting some of the simple stuff like why is B to the left here, it's probably because you didn't carefully go through the material from last week. Everything we're doing is building, and if you're not strong in what we did before, you're going to be confused and lost on what we're doing now. All right, let me do one more of these. This is a negative charge, by the way, so let's go ahead and just don't forget this is a negative charge. All right, just to remind you and myself, this is a negative charge. And what is this showing us? Well, let's look at the magnetic field first. The magnetic field is going from north to south. It will always go north to south outside of a magnet. And the charge is right here. That's where the charge is, where that red dot is. And I'm showing the velocity of that charge is into the page. The circle with the X through it means that there's an arrow into the page. And since it's labeled with V, we know that the velocity is into the page. So V is on the negative Z axis going into the page, and B acts on the charge, or B at the location of the charge, which is negative, is to the right. Alright, so the force, right-hand rule, will give us one direction, but since it's negative, don't forget we have to flip it. So let's see. When I use right-hand rule, I get that the force is down. The force is down, but because it's a negative charge, we have to flip that 180 degrees. The force is up. Okay, right-hand rule did give us down, but because it's a negative charge,